Swayam Prabha. Digital India. Educated India.
Today the lecture is on friction. For your reference, this is module 4, lecture 9 of the web-based engineering mechanics course. In all our preceding discussions, we have assumed that the contacts between two rigid body surfaces are either smooth, that is they are frictionless, or they are fixed, that means there is no relative motion. But in practice, between any two contacting surfaces of a rigid body, tangential forces develop that we call it as frictional forces. They prevent the relative motion between the two and offer resistance to some degree before a motion impends and starts. This is for all surfaces irrespective of how they are smooth, though the degree of resistance offered for rough surfaces are more and for smooth surfaces it is less. The origin of these frictional forces are primarily due to the non-uniform nature of the contacting surfaces in the microscopic levels. Let us take an object A which is in contact with another object B. Let us say this is the weight of this object. So, if we consider microscopically a portion of this contact, there are undulations on the surface of both A and B. And the contact actually happens at few of these places and not as seen macroscopically. So, at these contact points, the intensity of the contact forces are large and they lead to deformation and thus interlocking of these material features. So, for the object under stationary condition, the sum of these, let us say the reactive forces which are happening wherever the two surfaces are in contact, the resultant of all these forces has to be equal and opposite to the weight of this object A, so that the equilibrium is maintained. But let us assume a small force now acts on this object A. Since these material features resist the motion, so these reactive forces change, the point of contacts may also slightly shift, their orientation will also shift, so that the resultant of all these forces is having some horizontal component also. If P is the force, then if the horizontal component of these reactive forces is F, it balances this force P, and this happens only for small amounts of horizontal force P. As this force increases, ultimately these material features deform and no longer the interlocking is maintained and the object A starts moving or sliding on the object B. So, these frictional forces are limited and they prevent only motion to certain degrees, and if the forces are large, then the motion actually takes place. The kind of friction that we just saw is called as the dry friction, or the friction existing between two surfaces directly in contact without any fluid interface. But in mechanisms or machines, we have lubricated surfaces where a film of a lubricant is present between the mating parts to reduce the friction. And to analyze these problems, we need to also take care of the fluid friction, or the friction between successive layers of the fluid, the resistance offered by these layers of fluid for the relative motion. But in the current lecture, we will limit our scope to dry friction, that means the friction existing between non-lubricated parts. The frictional forces that are developed are governed by certain laws. So, we will see that by considering this example. We take a block of weight W which is being supported by the surface B. When there are no horizontal forces, the weight of this object is balanced by the normal reaction. When a small amount of force P acts on this body, then a corresponding amount of frictional force develops between the contact between A and B, and this is what we call as the static friction, because the object is still in rest, and so this frictional force that is developed is the static frictional force. And as this force P increases, this frictional force F also increases to a maximum limiting value, and that limiting value, if we call it as Fm for a pair of surfaces, then the same is related to the normal reaction by what we call as the coefficient of static friction mu s. This has been found by series of experiments. and further when this force P is increased, the block starts to slide and the frictional force drops to a lower value and remains constant, and that frictional force which exists when the body is in motion is known as the kinetic friction. Let us designate it as Fk, and it also bears a constant relation with the normal reaction N, and the constant of proportionality is mu k, which is the coefficient of kinetic friction. So, these two coefficients, that is the coefficient of static friction and the coefficient of kinetic friction, are dependent on the types of surfaces, the roughness of the surface that are in contact. So, this behavior of the frictional force is depicted by this graph. When there are no horizontal forces trying to move the object, there is no frictional force and thus the frictional force is 0. But as this horizontal force P increases, correspondingly the frictional force also increases to a maximum limiting value, which is given by mu s times of N, the normal reaction. And then when the body starts to move, it drops to a lower value and almost remains constant for the entire motion. It has been found that even for small changes in the velocity, the force remains constant, though at very large velocities this force can drop to a slightly lower value. This maximum static frictional force and the kinetic frictional force that we have seen are proportional to the normal force and depend only on the condition of the contacting surfaces, and they are independent of the contact area. This has been found by again series of experiments. So, in the entire region where the friction is developed, right from the body which is in equilibrium and which is static to the point when it impends to move, the behavior can be divided into 4 different regions. We have initially no horizontal component of the force leading to any tendency of this body to move, and so there are no friction. Let us say now we have a horizontal component of the force which is Px, which is smaller than the limiting value, which is mu s times of N. So, the frictional force F developed is equal and opposite to this force Px. Here one should know that this frictional force F is not equal to mu times of N. Mu s times of N is the maximum limiting value, and when the object is not in the impending motion state, this frictional force is less than that, and it is only equal and opposite to the forces that tend to cause the motion. So, here this force Px is balanced by this force F. When the motion is impending, at that case we have this Px equal to the maximum limiting force Fm. So, only for this impending motion case we have the relation between this frictional force which is equal to Fm and N as Fm equal to mu s times of N. So, one has to be careful in solving the equilibrium problems with friction, that if only the motion is impending, we can use this relation between the horizontal force F and N using the coefficient of friction. If we are not sure whether the motion is impending, then this relation cannot be used. And when the body is in motion, this force Fk is less than the force that causes motion, that is Px, and this force is equal to mu k times of n. Let us see an example. Here you see two rods AB and CD pinned at A and C. They have a uniform weight of W and they are maintained in a position by the couple M0 at C. The coefficient of friction occurring between the contacting surfaces is 0.4. We are interested to determine the range of these moments which can maintain this equilibrium. We see that if this moment is large, then this rod CD starts rotating in the counterclockwise direction, thereby this point D starts moving against this rod AB towards A. If this moment M is small and is not able to support these loads, then this rod CD starts to rotate in the clockwise direction, thereby this point of contact D moves from A to B. So, we can consider the impending motion in the clockwise and counterclockwise direction in order to find the moments that are required. So, let us consider the impending motion in the clockwise direction. That means, this rod CD tends to rotate in the clockwise direction. So, to construct the free body diagram, we should know the direction of the frictional force that exists at this contact point. If we see this rod CD, when it tends to move in the clockwise direction, the point D tends to move towards B. So, the frictional force will resist always the motion. So, it has to be in the opposite direction of the impending motion. So, that means the frictional force will be from B to A. So, from this we can draw the free body diagram. For the rod CD, we have the pin reactions Cx and Cy, the applied moment M0 at C, the weight of this rod CD acting through its CG, and at D, since the impending motion is that the point D tends to move towards B, this force is against the same. So, the force is marked from B to A. On rod AB, this force will be equal and opposite. So, it is marked from A to B, and we have the pin reaction at A, the weight of the rod, the normal reactions as the other forces occurring in the free body diagram. So, from this, let us write the required equations to find the unknowns. We know that we are interested to find these frictional forces that exist when the rod impends to move and the required moment. So, we can take the force summation and moment summation equations, and for the impending case relate this F with this N using this equation. So, we see that we have a total of 2 unknowns here and 2 unknowns here, 4 plus 2, that is 6 unknowns in this equation, and we have additionally one moment which is also unknown. So, totaling to 7 unknowns, but we have only 2 free body diagrams, so which results in 6 equations only. So, for the impending case we have an additional relation, that is the relation between this f and n which are related by this mu s. So, leading to one more equation. So, the 7 unknowns can be found using these 7 equations. So, let us write only those equations which are of interest. So, we sum the moment about A and equate it to 0, and from this we obtain this normal reaction n from the free body diagram 1, which is equal to W by 2 cos theta, and we know the relation between the frictional force and the normal force. They are related by this coefficient of static friction. So, the frictional force becomes mu s W by 2 cos theta. Now, let us sum the moments about C. So, if we sum the moments about C, we have m naught, the moment of this weight which is W times L by 2 cos theta, and the moment of this force N whose moment arm is L cos theta, and the moment arm for this frictional force F is L sin theta. So, these are taken care in this moment equation, and by solving this equation we know these values, that is N, the frictional force F and W. So, we get this required moment, and the required moment is 0.818 times of WL. In the similar way, now we can consider the other impending motion. So, the other impending motion is that this rod CD has a counterclockwise motion. So, that means this point D tends to move from B to A, thereby the frictional force developed at this contact point is from A to B, which is opposite to the impending motion. So, for this impending motion case, the free body diagram is shown in this picture, because at this point D, for the impending counterclockwise motion, this D moves from B to A, this frictional force F is marked in the direction A to B. So, this completes the free body diagram, and again we have the set of equations which can be solved to find this moment, and in this case it has been found as 1.0484 WL. So, the range of moments for which these members are maintained in equilibrium is between 0.818 WL and 1.048 WL. So, we see that when friction exists, for equilibrium there are a range of moment values for which equilibrium is maintained. In certain problems, it is convenient to represent this frictional force F and the normal force by their resultant and relate the angle made by this resultant force with respect to the normal. So, this helps in certain analysis where this angle, what we call as the angle of friction, helps in the analysis procedure. Let us consider the same example of the block. Now, the applied force is vertical, thereby there is no horizontal component of the reaction, that is there is no frictional force, and so the resultant of the frictional force and the normal force is R, which is same as N. Now, let us consider a horizontal force Px acting on the body, and still this force Px is less than the limiting value of the frictional force Fm, So, the body is still stationary, and for this condition a frictional force F develops which is equal to this Px in magnitude and opposite in direction of this load Px. So, the resultant of this frictional force and the normal reaction is R, and now this R is inclined to this N. The angle of the same phi is given by this relation where tan phi is equal to this F by N. If the motion is impending, then this angle is equal to phi s, what we call as the angle of static friction, in which case the developed frictional force is equal to the maximum limiting force, that is Fm. And so, we have this tan phi s as F by N. In this case it is the limiting force F, and which is equal to mu s times N by N, and which simplifies to mu s. So, for the limiting case, the angle made by the resultant is related to the coefficient of static friction. So, if we consider the motion in all directions, that is in all directions of this plane, then we have this force R making a cone having a half cone angle of phi s. So, if the resultant is within that cone, then the motion is not impending. So, let us assume that there is a plane and there is a block, and this is the contact point. So, if the forces are applied such that this block tends to move in any of these directions, if the resultant of the normal reaction and the developed frictional force lies within this cone, say like this, then the motion is not impending. But when the frictional force reaches this limiting value, that is Fm, then the resultant lies on this cone, which we call as the cone of friction, then we say that the motion is impending. So, this kind of an analysis is sometimes useful in certain class of problems. Here we see a block in an inclined plane. So, the horizontal component or the component of the weight along the plane, if we take these as our coordinates, then the component of this weight along this plane tends to move this object in the downward direction. So, a frictional force develops which acts against this force, which is this Fm. So, we have for the limiting case this Fm equal to W sin theta and the normal reaction equal to W cos theta. And also for this limiting case, we know that this angle between the normal and the resultant force is phi s. From geometry we see that this angle phi s has to be same as this angle of inclination theta. So, for the impending motion case we have theta equal to phi s, which is equal to the angle of repose. And for this case again tan of this angle phi s is equal to the coefficient of friction mu s. And when the motion starts, we know that this reaction drops, that means its inclination comes down because the horizontal component of the force reduces and becomes the kinetic frictional force Fk, which is less than the applied horizontal force, and the angle of this resultant with the normal is equal to the angle of kinetic friction phi k. So, this angle phi k is related to the coefficient of friction mu k by considering these force relations. So, when we solve problems involving friction, we may have different situations. That means, we may be interested in certain cases to determine the coefficient of friction that is needed, or in some other cases we may be interested in finding the required force in order to cause a required motion, etc. So, let us see the class of problems. So, there could be class of problems where we know all the forces as well as the coefficient of friction that exists between the various surfaces, and we are interested to find whether the body will move or not. The other class of problems can be that we know these forces and we also know that the motion is going to be impending, and we are interested to find the required coefficient of friction. And there are other class of problems where we know this coefficient of friction and the condition that the motion is impending, and we are interested in determining this applied force which is required to cause the motion. So, let us take one example. Here you see a homogeneous sphere of radius r placed on this inclined plane. This is making an angle of beta with respect to the horizontal, and for any given position this hemisphere also makes an angle theta. That means, the diametrical plane makes an angle theta with respect to the horizontal plane. The coefficient of friction is given, the radius of the sphere is given. We are interested for the condition when this hemisphere starts to slide or impends to slide, what is the corresponding angles, that is beta and theta. For this body to be in equilibrium, the weight of the sphere which acts through its CG has to be supported by the resultant of the reactive forces that occur at the point of contact. So, that means the normal reaction plus the frictional force that is along the plane and the normal force, the resultant of these two forces should be able to support the weight of the sphere. So, obviously, the point of contact should lie just below the CG of the hemisphere. So, this picture shows the free body diagram of the hemisphere, the weight of the hemisphere passing through its CG and the resultant of the normal reaction and the frictional force passing through the point of contact A, which is lying just beneath G. From this geometry we know this GC, which is nothing but the location of the center of mass, which is equal to 3 by 8 times of r from the diametrical plane, and this distance AC is nothing but the radius of the hemisphere. And from the geometry we also see that the angle between the resultant r and the line AC is equal to this angle beta, which is nothing but the inclination of this surface. For the impending motion case where the hemisphere starts to slide along the incline, this angle, that is the angle between the resultant and the normal to the inclined plane, is equal to phi s, the angle of static friction. So, since we know the coefficient of the friction as 0.30, we can determine the value of phi s, and that is equal to this angle beta from geometry. Now, we have to find for this geometry what is this angle theta. To find that, let us consider this triangle AGC. So, this picture shows the point of contact, the CG, and the center of the hemisphere and the various angles that are involved. So, from geometry we can see that the angle between the horizontal and this diametrical plane is equal to the angle between this line GC and the vertical line, that is GA. So, this picture marks the various angles theta and phi s. So, from this we get this angle ACG, the angle ACG as theta minus phi s, because we know that if we consider this triangle, if this is the angle theta, then this angle is also theta. So, this angle is theta minus phi s, and this angle AGC is nothing but this total angle is 180 degrees. So, 180 degree minus theta, and we know the relation that sine of the angle divided by the opposite edge of the triangle is equal to the sine of the other angle and the other edge. So, the relation between the sine of the other angle and the opposite edge. So, we take this angle opposite to this edge AC, that is sine of 180 minus theta divided by AC equal to sine of this angle phi s divided by this length GC. Since we know these dimensions GC and also we know this dimension AC and we know this angle phi s, from this we can determine this theta, and the same has been determined as 50 degrees. Let us consider another example. Here you see two cylindrical rollers, each weighing 20 kg, is kept on an incline whose inclination is 15 degrees. Their diameters are given as 300 mm. The value of coefficient for friction, both static and kinetic, are given for all the contacting surfaces. Now, an moment of m is applied to this cylinder in order to allow for these two cylinders to roll slowly down this incline. So, these are rolling such that they are rolling slowly down the incline. So, we are interested to determine the value of this moment m that is required to allow for this slow motion to be possible. So, in order to solve the problem, let us consider the free body diagram for each of these cylinders. Since these cylinders are rolling without slipping at these points A and B, the frictional forces that are developed at these contact points are less than the limiting value. But in order for the slipping to occur, because when these rollers, these two cylinders roll down, this point at C has to have a relative motion. So, at this point slippage is occurring, and since these rollers are moving slowly, we have to consider the coefficient of friction mu k, because it is not the impending motion case, but actually the motion is occurring. So, the frictional forces that are developed at this point of contact is the kinetic frictional force. So, with this, let us draw the free body diagram. We have the inclined at 15 degrees, the two rollers, at this point of contact for the roller, let us say the normal reaction is N1, and we have a frictional force F1 along this incline. Because this cylinder, if allowed, it will try to slip in this direction, and so the frictional force has to prevent this slippage. So, at this point of contact, the frictional force is upward along the incline. We have the applied moment m, the weight of this cylinder, that is mg, which is acting. Let us say this is the line connecting the centers of the roller. At this contact point C, we have the normal reaction, let us call it as N2, and since this roller is slipping at this point C in the counterclockwise direction, the direction of the frictional force is opposing the same, and the same is marked here. So, on the other cylinder, the direction of this frictional force will be opposite, and this will be the direction of this force N2. At this contact, we have the normal force and the frictional force and the weight of the cylinder, say mg. We should keep in mind that at A and at this contact point B, there is no slippage. So, we do not have the relation between the frictional force and the normal reaction. These frictional forces F1 and F3 are less than the maximum frictional force that is possible. So, from this free body diagram, let us write the equations. we can sum the moments about this point B in order to determine this normal reaction N2, and this frictional force F2 is related to this normal force by the kinetic coefficient of friction, because here slippage is happening and they are in constant motion. So, we relate this force to the normal force by the coefficient of kinetic friction. So, let us write the equation. The moment summation about B and equate it to 0. So, we have minus N2 times the moment arm. We know that these rollers have 0.3 meters diameter. So, this radius is 0.15 meters. So, the moment arm for this force N2 is 0.15, and this force has a moment about this point B, which is equal to N2 times of 0.15. Then we have minus mu k times N2, which is so this force is positive, this is a negative force, mu k times of N2, which is this force F2, which is also having a moment arm of 0.15. Then we have the moment due to this force, which is plus mg sin 15 into 0.15. So, from this we get N2 as 33.85 newtons. Now, let us consider the other free body diagram and write the moment summation about point A. So, we have sigma m A equal to 0. So, we have this moment which is a clockwise. So, we have minus m, then the moment of this weight mg about this point A. So, we have plus mg sin 15 degrees, the moment arm for the same is 0.15 meters plus N2 times 0.15 minus mu k times of N2, which is the frictional force F2, times 0.15 equal to 0. So, from this we determine m as 10.16 Newton meter. So, this is the required value of the moment in order to allow these cylinders to roll slowly down the incline. So, these problems of simple contact nature can be solved in similar sense. The simplest machines that use friction in order to do some work are wedges. These are devices that are used to raise loads or to keep loads in certain position. So, they advantageously use friction to accomplish this job. So, here in this picture you see this block A, which has to be raised or supported in this position. So, we use these wedges C and D in order to accomplish this task. A typical problem could be that we are interested to find the force P that a human has to apply in order to keep this block in this position or to raise this block. So, in order to analyze this problem, we have to consider the free body diagrams of the individual blocks and wedges and represent the frictional forces in proper sense. That means, we need to know the impending motion direction in order to draw these frictional forces in the free body diagram. So, let us now consider this wedge C, which is being pushed by the human by this force P in order to raise this load or to keep this load in this position. Since the wedge tends to move in the direction from left to right, the frictional forces on these surfaces will oppose this motion, thus they will be acting from right to left. So, let us mark this on the free body diagram. So, we have this block and the free body diagram of the wedge. Since at both these contact points this wedge C is trying to move from left to right, these frictional forces oppose the same and thus they are marked from right to left. These are the normal reactions, and for the impending case this can be related to the normal reaction using this coefficient of friction mu s. Now, once we know this, we can now construct the free body diagram of these other two components, that means the wedge D the frictional force F3 is acting in the opposite direction, and we have this normal reaction N3. We have the normal reaction on this face and the reaction from the wall. Now, we can consider the free body diagram of the block. So, on the block face this force F2 is equal and opposite to the same. So, it is marked in this direction. We have the normal reaction and the weight of the block, and since this block is tending to rise against this vertical wall, we have this frictional force opposing the motion. So, we have this force F1, and for the impending case this can be related to the normal reaction by the coefficient of static friction mu s. So, once we construct these free body diagrams, it is possible to solve for the same.